Okay, so I'm going to begin my introduction while we have last couple folks grab their food. So welcome everybody to our first Stack FA Talk Fall 2025 semester. My name is Alexander Coulter. I'm the Stack FA organizer for this academic year. Fifth year PhD student. It's my honor to be serving SGSA, and another role. It's really something that we can't do without the help of a lot of students within this department. And as you attend our talks, attend our different events, I encourage you all to consider joining for the next year officer board so that we can continue offering such great services, great opportunities to network and socialize for all the graduate students in the staff department. Our first speaker today is Dr. Bani Mallick, who is a distinguished professor, Regents professor, and Susan M. R7 chair in data science and computational statistics here in the Department of Statistics. Dr. Mallick is the director of the NSF Tripods Institute of Data Science and the Center for Statistical Bioinformatics. He is an elected fellow of the AAAS, ASA, IMS, ISI, and the RSS. It's quite the collection there. And he's been a recipient of the Distinguished Research Award, the Distinguished Graduate Student Mentoring Award at Texas A&M, and also the Young Researcher Award from the International Indian Statistical Association. And in line with his extensive publication history, both in books and research articles on subjects of Bayesian semi-parametric methods and partition methods, his talk is going to be focusing on local models with partitions in Bayesian framework. And also, Dr. Mallick is going to, I believe so, be the next head of the department come January. So I hope that everyone gives Dr. Mallick a warm welcome for our first Stack FA Talk.
Howdy. So it's a significant day in my life. I'm giving a technical talk after 25 years. I came for interview in 2000. I gave my first, and that's my second talk. So it's a 25th year of my technical talks. I never gave any technical talk in the middle. Second thing is a significant day for the college also. There are a lot of changes. So possibly this is my busiest day. My meeting started from 8 o'clock, from president office to provost office to here, and it will go on. So everything is together. So this is a significant day. Anyway, so I know most of the faces from my Stat 632, and today
Sorry, I just want to make sure that when you start here.
The lecture I'm giving today is what I'm doing for last 25 years, because it's 25 years. And it's, I try to keep the technical details very mild, like it starts from starting 632 things. And some of you see that your exam questions are here, right? So, and then it goes up, and I try to tell you why I'm spending 25 years for this research. It's a big span of research. And this is more philosophical rather than technical. So these are my co-authors. It starts from Chris Holmes in 2000, who graduated, who is now a professor in Oxford, pretty big guy in Bayes. Then it stopped, he got savage, and then it got stopped for 10, 12 years. So that's a historical fact. Suddenly it started again with Nilabjo, Richard. You have seen some of you, Richard, fantastic student, Yabo, and this started 2010, 12, suddenly it came back. Why there is a discontinuity, I'll tell you. And then now it took much more pace when I have seen Zhao Tang, Valeria, Srijato, Somjit. They started working on some of the recent problems. So there is another jump. So these are bumpy things. And also faculties here, Vian and Yang, always my collaborators, especially with the recent work. So why you have to do it? Why local models? Why I'm spending this time? Once upon a time, there was a model called linear model, right? So why we love linear model, all undergraduate classes, in fact, high school classes start with linear model. Beautiful interpretation. I have slope, I have intercept, I can estimate it, I know meaning of every parameter. Why it's bad? In life, nothing is linear. If you tell one variable going up, other variable is going up too, it's never going to happen. So then spatial, some of you are doing spatial stuff. We do simple assumption like stationarity. Stationarity telling you that more far you are going, correlation is going down. But it doesn't happen in complex data. We'll show you some data where 2 points could be very close, but there is no correlation. When as a student, I got some data like wind data from Greece. Two cities are next to each other, but there's a mountain in the middle, so there's no correlation. Okay. So that's the kind of complex data comes in, and simple models start failing. So you say, okay, now we go to computer science. It's a cool term. Why don't you use deep neural networks? Why don't you use SVM? Why don't you use BART? Like all these big models there. So why you need local model? The trouble is most of them are predictive models. These are black boxes. Input getting in, you are getting output. But there is no interpretation of parameters. Why I need interpretation now? Why suddenly I started talking about interpretation? This is the age of AI, artificial intelligence. You need to create a logical structure, then you can feed in your app. But you don't know what's going on, you cannot do this logical structure. A doctor, say oncologist, he can get patients. These deep neural networks tell, okay, I am giving all the information about this patient, how long he's going to survive. Beautiful, you'll know. But more he wants to know how the treatment will go on. What's the logic? What medicine? What you should check first? Those are the things. That they're not going to do. So why we do local model is it's much more interpretable than this black box model. It's much more flexible than this simple linear model or stationary model. So that's a main logic, and we'll see that. So what is local models? This is simple models, but it is fitted in a local region. Very simple example, all of you know from approximation theory. Linear model doesn't fit very complex curve, but if it is locally linear, say it's just piecewise linear. From approximation theory, you know, if you have enough number of pieces, it goes to any function it can be. It's dense in some class of things, okay? So that's the theme, that I'm using local model in some regions so that globally it captures any complex models. Local linear models are very famous. There is a Boy by Fan and Gibel, and all these things are there. But I'm not talking about only local linear models or regression. I'm thinking about a very big picture, local model. It could be local survival models, local proportional hazards model, local Gaussian processes. So whatever you are doing by model, I mean a big world class of model. You are doing time series, it's not AR model, it's locally AR. Okay, so autoregressive models. So that's the kind of theme I am getting in here. The model changes over the regions to accommodate complex structure of the data. So locally it's interpretable, globally it can capture everything. But the major challenge here is, what is local? How do you define? With problem locality changes. In 1D, you can say, okay, regression is easy. I can take intervals as locality. But what about in 2D? What about in higher dimension? So that's the main challenge, how you find it out. And another major challenge, if you really want to tune these models, you need to adaptively estimate this locality. If you say I'm fixing the bandwidth and I'm working with a histogram, it may not be that flexible, okay? So the data should estimate it. So that's the main challenge of this whole thing. So we propose, there could be a lot of local models there. We propose local model based on partitions. So you're partitioning the space and fitting these local models. Today we are doing supervised learning only. Unsupervised learning, semi-supervised learning, future research, a lot of you can work on them, like especially semi-supervised learning. What we mean that we have response Y, X is covariant. You can tell explanatory variables, you can say whatever your favorite term. So that's a framework. Regression, classification, survival models, lot of things will fall in this category. Okay, so that's the thing. There's a book, it's an old book. This is a book with Dave Dennison was my first student, actually. He's in London market. Chris is author and Adrian is a very big name in Adrian Smith. We wrote the book and there is a lot of introductory things there. And still I myself read the book. A lot of things are not explored. So we just give some images. It's one of the popular, possibly the book in this field. But at the end of the day, a lot of things we take it out and still we can work on it. While he told us a million times to update the book, but we all are too busy. So let's come out now in the notations. So by partition model, I'm defining in this way. I have y and x. I'm partitioning the data. I'm just partitioning the covariate space X in m pieces. How the piece will come, all those things we'll see later. And fit a separate model within each piece. So two steps you can think. I have this X. I'm just slicing this X. Then I'm fitting Y within each of these partitions. And that's partition model. That's part of local modeling. We start. So that's a function we are writing. Probability of Y given partition is between partition, the data is independent. That's the assumption. You can ask why I'm assuming it. Yes, please. Yeah. So you have any pen. This room is special because you never get a pen here. So anyway, so do you have a? So what you are doing is, so you are going to suppose you have y and x, our good old example, 1x. You come here, here x, here y. The partition is limit sets, just intervals, and you're fitting or whatever you want to do. 2D, I'm slicing say x1, x2, right? So I'm partitioning this, suppose some geometry thing, we'll learn later. Then I'm fitting here spatial models within this region. So that's partition model. And the basic assumption here is given partition, the data is independent. There's a big research problem, it could be here, that why you make it independent. Future people can do dependent, but that structure works to write a likelihood function and stuff like that. Basic structure, you can think it's like an ANOVA model. So what do you do ANOVA model? ANOVA, you have group 1, group 2, group 3, right? And you have data. Now what you are saying that within ANOVA model, between these groups, they're independent, right? And within, you put some models here. And if you think about ANOVA, this is like a partition model. Only the difference is the group is determined here because you're doing the experiment. Here I'm learning the group, like clustering kind of thing. So that's the basic assumptions of this whole model. Anytime you think it's like a static study to class, stop me and ask questions. Please feel free. So what you do is so there are two things. Between partitions, they're independent. Within partitions, that means I'm thinking about data here. You can think they're exchangeable, whatever exchangeable or conditional independent. That's the starting of ANOVA model. But we can put a lot of dependent structure. It doesn't need to be ANOVA. It could be MANOVA, multivariate analysis of variance, like they are multivariate Gaussian. It could be spatial. It could be images. So it can be extended, and it has been extended. So I don't want to show the slides, too many writings, but at the end of the day, what it's telling you, a partition model is made up by splitting the covariate space X. Only I'm partitioning X, the covariate space, not Y. And then I'm fitting Y within this covariate space. So rather than writing a structure Y equal to X transpose beta, I'm getting the covariate through this partitioning, the whole thing. That makes things simpler. The response Y within each region is assumed to be exchangeable or non-exchangeable, doesn't matter. And the main motivation is points nearby in covariate space come from the same local distribution, so locally. And naturally usually these models are fantastic to get sharp changes. When your functions, suddenly spike comes in. It's a change point model. Now you say, okay, this is a regression, all the example. No, the first example I got from petroleum engineering. They have flow of oil and they dig. So I have a paper, I forgot, when to dig or not to dig. A big $1 million question, actually. If you dig, if they ask us in the data, should we go and dig to get oil or not? To dig, it's millions of dollars. If they don't get all, it's all lost. But if they get all, they make billions. So it's a very big question. The main problem is all petroleum engineering takes our stat courses, and they know spatial modeling means spatial Gaussian processes. But the trouble is, it's not like that. There are so many rocks, this, that, very sharp the space changes. We call sharp non-stationarity. I have a JASA paper that time. I should give when Moon Kim's, it's a Kim and Mallick. That's called piecewise Gaussian process. We derive this piecewise Gaussian process, where this is not one single, the covariance structure of the Gaussian process is changing. And they used it actually in their simulator, this piecewise Gaussian process. So, but this is very simple. So, you go tell Dr. Mallick, can you give me 2 lines? These are all graphs, all notations graphs. Can you give me 2 lines how to fit these models? Yes. First step is create the partitions. Here, somewhere you create the partition. Then once you know the partition, develop model within each partition. But the learning is don't do it in 2 steps. There is a lot of people try to do. They create the partition, fix the partition, try to do this thing. You get biased estimate. You have to do jointly. And whoever have taken my Stat 632 course, you have heard it repeatedly that you need to do it jointly so that a joint model comes to the hierarchical structure. All right, so there are 2 parts. So if you want to do a research in this field, you can do 2 together or you can do separately. And my students are divided in that way. Some students work on how to create the partition. Chris Holmes started and then Ian Moon all did with Voronoi tessellation. In high dimension, when you don't have the interval, they started with interval. Then they created some Voronoi tessellation with special pace and stuff. Voronoi is great. We'll see some Voronoi tessellation. But the problem with Voronoi tessellation is to very high dimensional X, it doesn't work. We also did binary trees. Binary trees, why it's better than Voronoi in a way, why it works on high dimension, we'll see that we do it in marginally. We don't go for x1, x2, xp together. If you have 100 covariates, we take x1, we do x2, and binary tree is beautiful. I'm loving more and more. If you do AI, where you do artificial intelligence, you want to create a logic. We'll see an example. Binary tree creates a logical tree. And then there are spanning trees. It's special. There are points which are non-stationary. A lot of new students are working on spanning trees, which is, with the work with we and where we created this thing. The 4th one is more exciting. Shomdeep, I think he's working on extending binary trees. Binary tree is 0 or 1, yes or no. But now we are putting more operators, plus, minus, percentage, power. Why? Because we can discover scientific formulas. My question is called scientific machine learning. My question is, do you need Newton or Einstein? Or data science can discover all those formulas, say gravitational rule. Suppose Newton is sitting under the apple tree, got an apple on his head, start thinking all these gravitational rules. Suppose I'm a data scientist. I just sit there and go on taking data. The apples is falling 1,000 data points. Would I find out the same formula by using data? That's scientific machine learning. Good news is yes, read that paper. We just Shomjit and we wrote that paper. Any formula, that's simple. Any physics formula, any material science formula, materials comes together, there's a V chemistry formula, but data can tell you. So there's a scientific community, there's a machine learning community, and they're merging some way, and that's called scientific machine learning. Because in future, we may not have time to do experiments, they're too expensive. But data can find out some of the scientific formula. Okay, so that's another field of research we are doing. So okay, so models within partition. We start with regression, Gaussian model, with conjugate prior, by God, that's 632, my favorite. Then we did classification. We did CART, Bayesian CART. We did Dave Denison's paper, and then Chipman, Ed George, lot of times talked about it. We did simultaneously this Bayesian CART, which is very, very popular, got a lot of references. Those are all in 2000s. The major challenge, all this problem is to identify the partition. Believe me, all other things are local models are simple. They're linear model. They're Gaussian process model. Everybody knows that. But where? How do you know which intervals to go? How you determine the intervals? How do you know how many Voronoi tessellation do you need? What will be the shape of them? That's the main thing. If you can do within partition, you have simple models. Okay. So first we started historically how the history goes on. The research started when you have a simple conjugate model. Simple conjugate model means what we did in our 632 class. Okay, exactly. And all of you who passed that class or summer exam, you got it. The sad thing about becoming head is possibly I'm not going to teach that course anymore, at least not for the next 3-4 years. Somebody else will teach. But otherwise, I could give you your summer exam. Whoever are the new freshers, I'll tell you'll get an exam question like that in your summer passing exam. Okay. So, so this is regression, like, you have notes, class notes, y equal to x beta plus error. Remember? So what is the conjugate prior? Believe me, if you want to do anything sparse prior, sparse penalty, this is starting. Doesn't matter. This is called normal inverse gamma prior. And this is my class notes. And probability one, you'll get a question like that in your summary. So if I taught, that's a question in your summer exam. Now I'm not talking about class exam. This qualified, you are going to get a question because this is so good. It's so cool. So what it's telling you that I'm putting a prior. If you're not a Bayesian, doesn't matter. Why I teach these things? If you're not a Bayesian, you do sparse penalties, right? Sparseness, all of you know. Bayesian put Laplace prior, and if you are not, you put Lasso penalty. We showed in our paper Lasso and Laplace prior is there. Then there's the horseshoe prior, scale-mixture prior, all these things and penalty scale. Everything can be linked with this prior, and that's in the 632 I usually teach. So this is a prior. Again, if you're not technical things, you say it's too tiring, food is much better than the slides, you can concentrate, but this is the way you start doing it, okay? Then the question is, again, I told you once upon a time there was a linear model and there's nothing linear. Doesn't matter. Everything is locally linear if you work with regression. Everything. Approximation theory tells you. But the trouble with maths is it tells you about existence. It tells you that if you have perfect piecewise linear, it can capture any curve. What is perfect? Asymptotically, you get lot of intervals. With finite data, what is asymptotic? Where are the intervals? How many intervals do you need? That statistician solves. So I'm thinking about curve fitting. That's we started in the model. Y equal to fx plus error. So x is no more linear, it's non-linear. Then f is an unknown function. But I can use linear basis function there, right? So here I'm saying that if I have something only y and x, so I have this. I can piece it up, this, and here I can put a quadratic curve, or make more pieces, put a linear curve. So I can partition the space and put very simple function, but it can approximate this function. Approximation theory is telling existence. It's telling you always you can do it, but mathematician never answer how to do it. Rendezvous is a very big approximation theorist. And always we have a talk, and I always say, Ron, you give existence theory, you don't give an algorithm. You never tell how to do it. And they say, that's your job, Bani. I don't want to steal your money. So that's always goes on with approximation theories, but that's fantastic. If you get a time, if Ron still teaches his approximation theory class, sit there. He calls something called constructive approximation. He's famous. There's a journal in his name, constructive approximation. He says approximation theory is very abstract, but he says do this for engineers, you'll always get a result. So he constructs the whole approximation theory anyway. So this is called, I know Ron because he was one of my PI in tripods. So what we do is we do simple basis function and piecewise linear function for doing this thing. What I'm doing here is I'm writing it as a linear model. Only thing is here there are some knot points. Knot points are like change points, what I show you. That's theta 1, that's theta 2, that's theta 3. So I have knot points. And within the knot point, this is just a line. Very simple, and you all know that. Like splines and everything is a part of it. So thetas are knots. Beta are the regression parameters within each of the intervals. So I have this curve. I'm doing these things. I'm putting this is theta 1, this is theta 2, and approximating it by line. And these are the slope and intercept. I have a lot. Question is, how many knots you need? What is K? I don't know. Mathematicians leave me. They say, hey, if you have a perfect K, but what is, if K is very large, how large is large? I don't know. Similarly, what are thetas? What's the location? I can take uniform, then maybe you get too many parameters there. Can I adaptively estimate them? So that's my design matrix. Again, if I give an exam and you have to take it, always I give you a linear model, give you the problem. This time I give you change point problem. Possibly you write your design matrix and write y equal to x beta plus error. Okay, so that's my design matrix, x beta plus error. What is the difference between what you take in your linear model class and this? Anybody can tell me? Suppose I have once upon a time, I have this linear model. Now I wrote this linear model. What's the main difference? The main difference is here within my design matrix, I have parameters, theta, b. Usual linear model, all my parameters are regression parameter error variance, but x is also containing parameter. Those are the not points. That's the challenge here in this linear model, that I have a y equal to x beta plus error, but my x contains parameters, major parameters. Here, betas are nuisance, I don't care. So how we handle it? We say, okay, we are Bayesian, so what you do, again, I'm not going to Bayes theory. You just write down your unknowns and you write down your knowns. And the main thing Bayes learning is write down what you don't know. I don't know the regression parameter, variance, not points, number of not points, condition on whatever I have observed. That's posterior distribution. That's Bayes learning. I learn this way, I then write. I can write down likelihood. Again, the technical thing, all in the book and in the paper. I'm not going through. Say, trust me, some way you can do it. But the good thing is we are using conjugate prior here. We are using normal inverse gamma prior here. So what you get is you can marginalize beta sigma square nuisance parameter. And again, 632 class, you know that result. I'm not showing you. That result, if you cannot prove, you don't pass my 632 class. Right? In IG prior, what is the base factor? What is the marginal likelihood? You know, every student last 3 years did this calculation. And most of you did fantastic, okay? So the thing is, you see, I am getting marginal likelihood. I don't have beta or sigma square. Those are nuisance. I only have the number of not points. I have the location of not points. Exactly, mathematically, I can find it. I use that. Now the big question that time came is more philosophical. Here is the number of nodes of the dimension, and that is unknown in my problem. I'm estimating it. So we ask the number of things you don't know is one of the things you don't know. And that's a question always. Learning a dimension of a model is very hard. And that's we did it explicitly and we showed it's consistent. And there is something called algorithm. We are not rendezvous. We give algorithm, and there is a reversible jump algorithm. Code is there. You can use it. We have MATLAB code because MATLAB was popular at that time, but you can write down. Example, block function. Why you did get this function? That time in 2000, there's a very popular thing, is wavelets. Wavelet people say, oh my God, statisticians do only Hilbert space, only do smooth curves. Can you go to the next space? Can you do very rough functions? Can your spline method work? We have wavelet basis function that works. I cannot tell two bad things about wavelet. Bani is still head of the department. Before I become head, he can fire me. So, but wavelet, there is a Donahoe-Johnston paper which is extremely popular. They show wavelet is the way to go this kind of function because they have this very specific thing. And we ask the question, do you need to learn a new functional thing wavelet, or our good old piecewise linear can do it? So this is one of the simple functions, they're block functions. What we did, we make our algorithm over this function. That you see here, the red is the true function, fitted function, blue is the true. There's some noise. You cannot separate them because we exactly did it with our method. So we are doing kind of what wavelet can do. We did better with their own function. It's not our function. It's Donahoe-Johnston's function. Not only that, what we can get? We can get a distribution of the not points, so whole uncertainty. The not points, it can take different values. And this is the distribution. It's 14, 16. That's called complexity. More not points you need when it's, suppose I have one linear model. I use my code. What will happen? You have no not points. Only one line can fit in. If you have two, but adaptively, you're learning. You have a lot of data these days. You can learn. So in this graph, you see, we need around 16 not points, but we get the whole distribution, whole uncertainty quantification of this complexity. This function, one of the hardest function in Donahoe-Johnston paper, just spikes. Try to use any of the spline methods. It will fail badly because it's not at all smooth. Okay. But if you use our method, piecewise it takes. But how do we capture these things? Look at number of knots. Now rather than 69, it's 78 number of knots. But that's I'm not telling you. I'm learning. What's the time when I should stop?
Probably around just before we break, so it's going to be about 20 minutes.
20 minutes already. So that's the way you learn. And the best thing about this paper is you can learn complexity from the data. And that's these days it works. Challenge, why? Then we stop. We say we solve the problem, mathematics solved, the blah, blah, blah. Why you work? The trouble, because we couldn't solve the other thing. This is 1D problem, y and x. What about high dimensional regression and classification? We have GRSSB paper where we use, rather than intervals, high dimension, we use linear planes, right? Line become a plane when you go. So we did piecewise planes. That's a very good paper in GRSSB. Then we do partition with von Neumann tessellation, trees, but which everything depends on conjugate structure. Think about research. When you do research, think which part I have to hit. Here we say everything, all my algorithm depends on I can marginalize. I can integrate out beta, sigma square. I have a linear model structure. You have a non-conjugate structure. What I'm going to do? I'll give you two examples. Another is there are no theories there. Okay. Cart theory is coming out now. We just did a little bit. Veronica did some of the things, but theory follows the methodology. So we did everything conjugate structure because our algorithm depends on normal inverse gamma prior. That's why I teach you in the class. Think about density regression. Density regression is beautiful. Usual regression, I model the mean. Median regression, I model the median. Quantile regression, I model the quantiles. Density regression, I model the whole density function. The whole density function I model. So this is density in supervised learning. I need to know what is the distribution of y given x. The distribution is changing with x. Mean regression is only a very specific case of it. On Gaussian, it's sufficient, right? You may make your variance depends on x, but the distribution could be very, very different. So if you try to do that, many data sets, it doesn't work. How we get it? Student life, every time you remember, student life is important. That time when I was working with Alan Gelfand, he gave me some data with non-parametric Dirichlet process, and he told me fit it. So I was fitting these blind things. Error distribution, it has only one covariate, male or female, sex. Very simple. Why? With beta naught plus error. Beta naught is shifting. Can you believe it? These days, nobody works on that. But each time, the error distribution turns out like this. What it tells you? It tells you when you do simple linear model, you think the mean is shifting here to here. Male, female, high or low. Here the distribution is changing with covariate. For male, it's very tight, symmetric Gaussian. For female, it's becoming skewed. So possibly there's some missing covariates for females. So this is one of the very, very example when I found out when I was a student that covariate is not a mean or thing. Covariate is affecting the shape of the error distribution. Then when I became a professor in Imperial College, I started investigating more. We used polyetry, Walker, Mallick, Walker. We have multiple papers on biometrica. Then David Dunson and people followed and make those methods better. Okay, but why I stopped there? I got it, I know, I wrote some papers and stuff. I never work, and I'm telling you all, if you don't have a motivation, don't work. Don't tell that my advisor gave me a problem 20 years back, I'm still doing it because he told me to do it. No. I stopped because I don't have any motivation. Only male, female is not going to push me much. Then I came here, and from industrial engineering, I got windmills data. Windmills are huge now, right? And they create power. And what they do is, so they are turbines, lot of turbines which are creating, wind is coming, turbines moving, and it's creating power. So that's the whole thing. So what happens here is when the wind is very slow, nothing moves, no power. When wind is very high, it stops automatically. Why? It will break the whole thing in storm. So there is something called cutting speed, there is a rated speed, and it stops. So the curve like this, wind speed, it goes up. It goes up also the power, but here there's no data. Then it goes up all the way. Then the machine, the control technology, stop it because it doesn't want to break it. So that's the shape of this curve. It lies between 0 to 1 because they tell us to standardize. They don't give you the actual data because we can find out which turbine is better than others and competition. So they are always standardized dividing by the maximum value. So that's the way it works. We found that they have sensors, they have so many data. So it's not a wind curve, it should be a wind surface. These are all the predictors there in the sensors, but they never used. Their standard thing is just use IEC 2005, take wind speed, take power prediction, do a curve, and they do binning method. I'm not going through the binning method. Binning method is our histogram method. Just bin it by yourself and look at it. So that's the way you do. But what we did, now I'm coming conditional density estimation. I told you, Dunson and his group, oh, they have probit stick breaking, they have kernel splines mixture by fan, Superburger, there's a lot of methods there, but none of them can capture sharp changes. And here you have sharp changes. So I don't think we have enough time. And also, what we did here, I'm just giving you some example. Future, if you come over, I can tell you. What I told you in our modeling, how to partition and model within partition. Two things I have to do. If you know that, you know everything about partition model. Here, how we partition, we use Voronoi tessellation to partition. Why I did it? Because I have only 4 covariates. This is not genomics. I don't have 20,000 genes. Here I have only 4 core. But this partition works very well. And model within partition is, Gaussian process is beautiful for functions. But here I cannot use it. Why? Density function has constraint. It has to be positive. It has to be integrate to 1. So there is a model called logistic Gaussian process. Logistic Gaussian process is a part of Gaussian process. It's exponential Gaussian process normalizing it. It works very well. It's completely non-conjugate. Nobody, Gaussian process I can marginalize. Nobody knows how to do integrate logistic Gaussian process. So all of you know what is Voronoi tessellation. We have a code also for Voronoi. So Voronoi tessellation looks like this. Our specialty is Voronoi tessellation mathematician uses a geometric structure. We are using as a modeling trick. So I'm saying, okay, this is good, but I don't know how many centers are there. I don't know how many pieces are there. I don't know what the shapes of the Voronoi tessellation. All I'm learning from my data. Okay. And that's the model. So if you talk about Voronoi tessellation with computer scientists, they just use it for finding it out. For us, we are doing inference. For them, it's a way to plot figures. So this is logistic Gaussian process. You look at it, this is a density function. F is Gaussian process. You exponentiate e to the power fy, and then you to the integration so that it follows all the density functions properties. And it's very popular thing. But main problem is in this likelihood. Again, what we did is piecewise logistic Gaussian process. We are piecing it up like this, and then in each one, I'm using that function. Again, let's forget, we have to marginalize this posterior thing. What we did is something we did in the class. I want to show you that what we do in the class in future research you can do. That's called, I cannot marginalize exactly what we do, something called Laplace approximation. So all of you remember Laplace approximation. I don't give any question on Laplace approximation because always I get requests, it's too hard to do in exam, so it's okay. But this is a Laplace examination where you find out some map estimates and you do this thing. So the learning is now we move from exact marginalization to approximation with marginalization, where we can create our algorithm. At the end, you remember our job is to create algorithms. If we cannot compete with modern science. Okay, so we do, and we have some theoretical results because this is a very hard problem, but we showed that somewhere if you do these things, you get the right estimates. It's all in the biometrica paper, but theory was pretty hard, because you have a Laplace approximation there, but you need to prove all this consistency theory there. Anyway, I'm not showing this simulation. I'm showing you this result. We have 10,000 observations. We have all these variables here, and we are trying to find out this curve, estimate the curve. It works beautifully. This is the curve. All it's saying at the end of the day, it's frustrating, it's saying wind speed. Just telling you that this method also do variable selection normally because it only selects those variables where they are doing partitioning. Nuisance variable it doesn't touch. So here it turns out that wind speed and wind degrees are only important variable. It picks it up. Best thing is engineer got a shock because they usually hide this 12 meters per second where they stop this turbine to this maximum thing. Nobody knows it. Data exactly found it out. So it's piecing, it's all adaptive piecing, where this whole density is changing, and that's the maximum. Here it stops. So we told them, if you give data, you cannot hide this thing. This inside their control thing in the machine. We can discover what machine is doing through our method. And these are the density. In different regions, you see why we need Laplace, why we need this Gaussian process. In different regions, sometimes it's skewed, symmetric, completely like this, and a spike in the maximum points. Our method has the flexibility when you go to different regions. It's almost non-parametric, it's Gaussian process. It can capture different shape of density. It can do that. So it's a very, very flexible method. We are running short of time. Now I want to show you an example, binary tree. I tell you, if you have a lot of covariates, sometimes this tessellation can fail, but you can do binary tree. What is binary tree partition? This is AI. This is logic. This logical thing, partition is good, but we don't have a logic. Here we are creating a logic. What they do, they take every variable and try to ask a question, yes or no, binary, yes or no. And then they go to left or right and create some kind of logical structure in the model. That's the partitioning. Look at it. I have two variables, x1 and x2. First question, we call these splitting nodes, the elliptical. x2 is less than 8 or greater than 8. If it is less than 8, you say yes, you go left. If they're right, you go right. Then possibly you don't ask any question. That's called terminal node. In this direction, you ask another question. Do you think x1 is less than 4.8? Yes or no? So these are the questions which is moving you. Why it's important, I'll show you. But this question you are asking, this 4.8, you're estimating from the data. Which variable you are going to ask the question, you're getting from the data. And in terminal node, you have the distribution, Gaussian or classification distribution. Those you're estimating from the data. It's completely adaptive. And that time, our CART model creates a lot of things because this is called random trees. We are creating a distribution over the space of tree. That's not easy. If I ask you, can you give me a norm on tree? You cannot tell. Tree is very, very different than continuous models. But that time we define a metric and create a random tree. So we estimate from the data. Let's move from the method. We did it in survival model. Survival is completely, it has censored data. All of you know how much patients are surviving. Survival curve gives you. It's non-conjugate. You cannot handle it. It's very difficult to handle. Main theme is survival function. Survival function tells you how much. It's very optimistic. It's the 1 minus CDF. How much patient's death is happening in some region. That's people want to know when they do. So if you want to go to pharmacy or dose response model or anywhere, you need it. Do we have a course in survival analysis here? We'll have them, okay? So that's the way it moves. And from survival, we do something hazards. Don't look at it. It's not the time to look at it. We are almost done. But hazards function tells you instantaneous chance of death. There's a very big thing, Cox, David Cox proportion of hazards model. Right? You know, Imperial College, when I joined, he was not there, but previous head of Imperial College was David Cox for 35 years. Okay, so I missed him, but anyway. So that's the, but proportional hazard model don't work, and David Cox didn't hire me, that's why. The next Adrian hired me. All right, so let's go to an example. We did something called treed hazards model, whatever it is you can read. Just look at why I'm talking tree and AI is coming together. So we have dependent variable is time of death. This is primary biliary cirrhosis data. This is a liver problem, so and people die. So there are 276 patients, lot of censoring things. Covariates are treatment group. What treatment group you are using, age, sex, edema status, serum bilirubin level, and CART also do variable selection. It only selects the thing which you are needed. That's the curve I get. So I'm creating a robot doctor. I don't need a doctor. I just give it through my app. So what a doctor should do if they get a data, it look first to the bilirubin level. Here, that's the part he should look at. Is it less, so he did all the tests from the patient. Is it less than equal to 1.9 or greater than 1.9? Binary. Yes, it's less than. You are lucky. The survival function is so good. It's almost 1. The death is falling very slowly, right? So you're good. Doctors say, go back and drink more. Not so, but anyway, something like that. But suppose bilirubin level is high. More high is how high? We are estimating from the data. Okay. So what it's telling you is high. What you should you start crying? No. You look at edema status. Do you have a lot of swelling, water? If you say that edema is 0, means not present. 0 means not present, 1 means present. If it is present, you have high bilirubin and edema means you have a lot of swelling. You are in a bad stage, bad class, where the survival function compared here. You're surviving so long here, you're dying so quickly. You are in a bad shape. Now the doctor starts drinking. Suppose now that bilirubin is high, 1.9, but edema is not there. Then he asks more questions. He asks again that bilirubin is that high, it's high, but is it more than 5.7 or not? That's a cutoff. If it is more than 5.7, again the condition is very bad. But if it is not, then you look at age. Look at this robot doctor who knows all these logical things and he's creating it. So I don't need a doctor, replace doctors, get apps, right? So that's artificial intelligence. And you look at the age, if he's too young, again, the survival functions are good, but he's more than 45, then it goes down very fast. And this is for a simple example. Any cancer patients, we can create a app, startups, like you don't go for a job. Create this kind of statistical methods you're learning from here, use it. Have a startup retire at 30, right? That was my dream, I never did it. Okay, anyway. So this is AI, because these days, you say, do you believe this number? Ian Johnston asked me, Bani, you are talking too much about statistics. I'm a very pro statistician. Computer science talk confidently, I also talk confidently. Statistician problem is they're always random. No, it could be 1.9, there are random. I say, why go? Try to confuse them. And if you cannot confuse them, confuse them. Never go back and say it could be or not could be. That should be your motto. Convince them or confuse them. So I say, don't confuse them here. Yes, if I have 2 million data, yes. And these days in AI, we have millions of data coming up. So anyway, I'll stop here. So you see all these things. Now what we are doing beyond partitions, we are going for spatial models, like, where the things are like this. Do spatial. 2 points are next to each other, but there is no correlation, very high correlation, non-stationary. Is that application? Yes. Spatial transcriptomics. This is the rat. Understand? 2 points are here, but there is no correlation. They're very close. So Gaussian process doesn't work. You need special kind of partitioning. That's one of the things. Other thing I told you, this is called graph spanning tree. Graph methods, it needs to come. And also other, we are going for, I told somebody is working, extending cart towards scientific machine learning, where you are asking not only 0 or 1, you are using mathematical notation. That's called operator learning. Mathematicians say operator learning. I'm using a lot of operators to reproduce scientific chemistry, material science, physics laws from data. And that will change the whole thing. Now I'm trying to replace, not doctors, I'm trying to replace scientists by data scientists. All right, fantastic seeing you guys. Another day I'll come back, possibly I'll talk more about what we are doing. Today, it's a great opportunity after 25 years to talk about all these bright people. Go on doing research, and we'll do more. Okay, thank you so much.
So we have an opportunity now to ask some questions. Do we have, let's stop screen share, bring up the chat as well. So folks on Zoom, if you would like to ask any questions, you may join in too, but we have maybe about little over 5 minutes before we start cleaning up. Do we have any questions for our speaker?
For the technical things or about the future of the department, you're allowed to ask any question, yes.
Clarification of slide 68 when you are showing that tree.
Uh,
So, here you are using the tree to partition the data and all those plots you are showing, like they were different Fox models?
yes. So what we are doing is we partition the data, then when you're doing the terminal nodes, we are putting this exponential Gaussian process, non-parametric methods within there and estimating the survival function complete non-parametrically. That's why you get these things. Cox model don't work here because proportional hazard model assume that time of death and covariate has no interaction, right? And it never works in real life. There is a huge interactions like in here. So we are not using piecewise Cox model. We are using non-parametric models like a exponential Gaussian process.
You have to do this simultaneously, the partition
Yeah,
and
yeah.
modeling. So are you putting something in the tree impurity?
No. We are writing a likelihood function conditional on these things. Then we marginalize all these things using Laplace approximation. So it's in biometrics, already came out, and also showed that it's consistent. If you do that, always you'll find it out the right survival functions. Any other question? Could be from here, could be about the department, could be for future research, anything. Yes. Or number of knots? That's a fantastic question. It's very much depend on what prior you put. If you put a very, very vague prior, sometimes it can get a, so we put a truncated Poisson. So we say it's a Poisson distribution, but we say it cannot be. Like we have 200 data points, so we don't want 200 knots, right? So we say, okay, 30 knots, but it's adaptive, like in some way capture the whole thing. Speed is fast, yes.
Yeah.
Yes.
Oh, sorry, was the location on the?
Yeah, so given the knots, then we put a distribution over the location, which comes from interval theory, some kind of distribution we put it there. Look at our book, very well written there, right? Okay, so book is better than papers. Yes, please.
So the number of the knots is still a hyperparameter that we need to do some grid search or random search?
Number of knots is a hyperparameter. You're exactly right. But when you get the marginal likelihood, marginalizing these things, then we are doing MCMC kind of thing to draw it. Like, so you're not maximizing.
Okay.
If you do maximize, then you will underestimate the uncertainty. Because we are giving the band of the function.
Yeah.
If you over optimistic, it's a very tight interval of the functions.
Oh, thank you.
Yeah.
Yeah, you feel pretty good.
I have a question. So are you able to actually use gift samplers for your instances on?
Yes, so if you marginalize all these things, but you need a metropolis kind of thing because the distributions are not exactly known, so not explicitly known. So you need to do, and that's called a reversible jump. But nowadays we are doing some variation, right? So some of the variation bounds we are finding out because if you have to fight with AI, if you want to work in Google or they say give something, this back forth doesn't work. The trouble with metropolitan tips, you go forward and backward. Computer scientists say that we need only forward, but we go back means it's reducing the computer cost is going up. That's why this variational bound, variational optimization works very well.
Oh,
you have another question?
Otherwise,
Yeah.
could you- yeah.
Could you give a little intuition about how you use the reversible jump to?
Oh, yes. So you have this, think of the regression model. I integrate everything in NIG. I have probability of K and the given the knots. For K, what we do is birth and death process. We create a birth and death. You add a knot or reduce a knot. Okay, and we keep it reversible. And when I know the K, I can always draw the, you don't need, the dimension problem, you need to create a birth and death process.
So we have one question from chat. Will the modeling choice be sensitive to the geometry of the local partitions?
Oh, that's a beautiful question. And I have to tell that, I don't know. Because with the application, the whole partitioning is very fixed. Because all my methods come out from application. When I'm doing this kind of energy data, we have 3 or 4, I used Voronoi. I did the survival with tree, not for fitting it. The partitions coming from logic. Doctor wants to know a logic so the nurses can follow this chart. So it depends more on the problem or scientific problem I'm trying to solve rather than what is fitting well. That's another way, like in the machine learners, more how we fit, predictive distribution, these, that are more interpretations. I ask them what you actually need to do. But for special model, yeah, you can try. But for special model, we tried different things because the prediction is the very big deal. And yes, our model always beat the other ones.
All right, I think that if it's quick, we might have time for more.
Is the future department head, can you talk more about like the plan about how to help PhD students to be successful, either in program and after the program?
Oh yeah. For the first thing is to be successful, you need more funds, so you will reduce the courses. Second thing is you have to do more research rather than taking courses. So my idea for new students, not this year, for next year, but Raymond is the guru, right? So he has to decide finally. I always think that, rather than taking 3 courses, you take 2 courses each semester, and third, like biologists, you rotate in labs. How do you know what research you're going to do, right? And that's why you're here. So the third one will be you go to 1 or 2 labs as a research credits and do it. Second year or second semester. Exam, you can take any 4 out of 6 and take the exam. Other 2 courses you can clear. Also, I found that we force sometimes our students to do theory methods. No, application is great. Application computation is great. So these 4 courses, you have option. You can go to theory methods track, or you can go to computation application track. So everybody is very good, only if you can do what you want to do. If I force somebody with a theory, computation guy to do theory and theory guy to do computation, we make a mess. So that's my thing also, to do this qualifier based on what you like, what you do in your future. Some of my students are outstanding applied people. We force them, and and then they didn't do that good in exam, but in future they're flourishing, they're doing the best. So we need to give credit to all students depending on their aptitude. But again, I'm saying the guru is Raymond here. You will decide what will be finally. And after things, what I'll do is, in every seminar, I'm trying to get a very big pharmacy guy or one industry. One industry guy will come. Possibly his presentation will be not research. His presentation is what they're doing in Pfizer, what they're going to do in Apple. All this my friends or our A or whom I know or others know. They'll come. This will be non-technical talk, but the whole day they'll spend with you, telling you what to do, what not to do. Third thing is a future dream. It may not happen in this university condition. I really want to do a statistics certification in management. What I heard from the company people who doesn't want to do academics, it really helps to get some management experience, some management thing. At the end, you do that. When you go higher up, no statistics, you only manage people, right? So if we can do a certification with MBA, like main school, where you take 2, 3 courses, like we give a certification in applied statistics, what about applied management to get? So you have a PhD in statistics or MS in statistics with a certification in management, that will really help you. Some of them will work, some of them will not. All right.
Okay, thank you very much again, Dr. Mallick. Have any more questions you think of, feel free to
Anytime, get in there or send me an email. Till 31st. After 31st, I'll have a big party. You guys can join if you like. We'll have a long hangover because that starts the hangover.
Thank you very much, everyone on Zoom too. I'm going to end the recording and
I'll
stop
be
the
delighted
Zoom
to
session.
talk about not only research I love to, but also I love to talk about what you think about the appointment, how we